All right. So today, all I wanted to do was work some example problems with you guys related to the material that we covered last Tuesday. So I've got this in-class assignment prepared for us to work through. And our first circuit is this guy here. And we're interested in finding the primary voltage and current and the secondary voltage and current for our transformer system. Okay. So the first thing that we are going to need to do is to convert our circuit from the time domain into the frequency domain. Again, this is nothing that we haven't done before. So I'm going to come down here and do just that. Okay. So here is our sinusoidal voltage source, Vs. If we scroll up here, we're told that our voltage source is 45 cosine 200t plus 35 degrees. So how would I represent that signal as a phasor in the frequency domain? Not just the 200, but you're close. So it'll be 45 angle 35. So we just keep the magnitude, keep the phase angle, and throw everything else away, right? So here's our magnitude of 45. Here's our phase angle of positive 35. So this is literally just going to be 45 angle 35 degrees volts. Okay. Now we have a 5 ohm resistor. And I hope we all remember that the impedance of a resistor is just the resistor value itself. Then I have my primary coil for my ideal transformer. Dot is on top. And then down here, I have a 15 millifarad capacitor. Does anybody remember how to determine the impedance of a capacitor? So the impedance of a capacitor, ZC, is given by 1 over J omega C. The 2 pi thing that you're talking about is when you're given the linear frequency, but we were given angular frequency here, so we don't need to have that factor of 2 pi. It's already built in. Okay. So for us, that's going to look like 1 over J times omega, which omega is always just this guy that's being multiplied by time in our sinusoidal expression. So this is 200 radians per second. And our capacitance value is 15 times 10 to the minus 3. I believe I've proved this to you guys before, but the units of impedance are always going to be ohms, which is why I'm not bothering with actually writing down the units here, because 100% of the time they're going to work out to be ohms as long as we go down to base units. So in my calculator, I'm just doing 1 over 1i multiplied by 200 multiplied by 15 times 10 to the minus 3. And I wound up getting negative J 1/3 of an ohm. If anybody else wants to throw that in their calculator and verify, you're welcome to do so. Yes.
For the omega, if it's given in radians, you have to like change it to degrees or.
No, not at all. So I guess maybe we should look at the units real quick just to prove why we don't need to put it in degrees or anything like that. Okay. So for what it's worth here, I have 1 over omega. So omega is an angular frequency measured in radians per second. So 1 over that is going to look like seconds per radian, right? Then I have my capacitance. Well, capacitance is measured in farads, where a farad is an amp second per volt. Since I have the reciprocal of farads, I'm going to have amp seconds in the denominator, and volts up here in the numerator. So we should be able to see that the seconds cancel seconds. Radians are a dimensionless quantity, so they don't really do anything at all. And what we're left with is a volt per amp, which is the same thing as an ohm, okay? So we don't need to do any conversion here whatsoever, as long as we're putting our things in base units, meaning instead of saying 15 milli, we're doing 15 times 10 to the minus 3. It's all going to come out okay, and it's always going to give us an answer in ohms. Okay. Any other questions about that calculation? Okay. So moving over to the secondary side of our system, here I've got my secondary coil, and we have dot on bottom. Here is a 2 ohm resistor. Again, the resistor values do not change. And then I have an inductance over here. Can anybody remember what the equation for the impedance of an inductor is? J omega L, exactly right. So that's going to be for us J times 200 times 20 times 10 to the minus 3. So if I put that into my calculator, I have 1I times 200 times 20 times 10 to the minus 3. And I get J 40 ohms. Now I'm going to go ahead and write down my primary and secondary voltages, primary and secondary currents, and all of that kind of good stuff. And I'm just basing that off of our circuit diagram above. So I can see that V1 is defined with positive polarity on top. And my current I1 is defined as flowing in, like so. And V2 is defined as positive polarity on bottom. And I2 is flowing into the undotted terminal, like so. Okay. So there are a couple of simplifications that we could potentially make to this circuit to make our life a bit easier, okay? So the first thing that we could do to make our life a little bit easier is we could lump those impedances together on the primary side and the secondary side, and just have a generic, impedance that has both a real and imaginary part instead of treating it like two elements, okay? So for this particular guy, I would simplify this first by saying, so my 45 angle 35 is going to stay exactly the same. And then now I'm just going to put this together and call this 5 minus J 1/3 of an ohm. So that's just me recognizing that that resistor and that capacitor are connected in series. And so I can just lump those impedances together, okay? And then here's my primary coil. And then here's my secondary coil over here. And this secondary impedance is going to be simply 2 plus J40. Like so. Now, I have intentionally not drawn the dot on my secondary side yet because I'm going to mess with that a little bit, okay? So I've got my dot on the opposite side, but I also have the positive polarity voltage of that V2 opposite the way that I would expect it normally. So essentially what I'm going to do, and you can imagine this in your mind, is we're just taking that secondary side entirely and just flipping it over, okay? So I could write that as dot on the positive side, where Now the positive polarity terminal of V2 would be on top. Here's the positive polarity terminal of V1. Here's our current I1. And we just need to make sure that our current I2 is flowing into the undotted terminal. So if I draw I2 like this, as it travels around that secondary loop, it's going to wind up flowing into the undot. And so what we have now is a system that looks exactly like the first one that we analyzed in class on Tuesday with regards to the polarities of our voltages, the location of the dots, and the direction of our currents. So we can use those relationships that we found on Tuesday. So we know that V1 is going to be equal to A times V2. I'm just going to write that down over here. Actually, I'm going to put a bar over it. It'll be the same relationship. So V1 is equal to A V2, and V2 is then equal to V1 over A. We also have those current relationships. So that's I1 is equal to I2 over A. And flipping that guy around, we would see that I2 is equal to A times I1. So ultimately, if we can find one of these voltages and one of these currents, and we know what the turns ratio is, we can find the other thing. So let's talk about the turns ratio real quick. So when I was drawing these pictures, I forgot to include information about the number of turns, but it is there on the actual circuit diagram up above, right? So there's 3 turns on the primary side, and there's 5 turns on the secondary side. So from this information, what would A be in this case? Three over 5. Number of turns on the primary over number of turns on the secondary. Yep, 100%. Just 3 over 5. Okay, good job. So what can we do now to help us analyze this circuit? Okay, so I think we can do one of 2 things. Okay, we can either refer that secondary impedance of 2 plus J40 over to the primary side, or we can refer that voltage source and that 5 minus J 1/3 ohm impedance over to the secondary side. To me, I would tend to refer the secondary impedance over to the primary side just because it's less work, okay? So essentially, coming down here as a third kind of simplification, here's my primary voltage, excuse me, not my source voltage, 45 angle 35 degrees volts in series with that 5 minus J 1/3 ohm impedance. And now I'm just going to have this connected with that referred impedance. So we're going to have to figure out what that is, where this voltage drop is going to be V1 and this current is going to be I1. And once we solve for those things, we can get V2 and I2 just by using our transformer relationships. Okay. So how do I refer this impedance of 2 plus J40 ohms over from the secondary to the primary? Well, let's go back in our notes here real quick. And it looks like we get to that part. Here we go. To refer our impedance over from the secondary to the primary, we simply multiply it by a factor of A squared. Okay. So this impedance right here is just going to be A squared times 2 plus J40 ohms which would be 3/5 squared multiplied by 2 plus 40i. And when I put that in rectangular form, I wind up getting 18 over 25 plus J 72 over 5 ohms. So are we all okay with that? So now, how can I analyze this circuit and find either V1 or I1? Because once I know one of them, I can get the other one very easily, just using Ohm's law. Absolutely. So we could say that I1 is going to be 45 angle 35 degrees volts divided by 5 minus J 1/3 of an ohm plus 18 over 25 plus J 72 over 5 ohms, like so. Okay. So I'm going to throw this into my calculator. And I got not the answer that I was expecting. Let me double check that J40 thing there. That seems kind of large to me. Yeah, sorry. I had an error. Let's see. This shouldn't have been 40 ohms. This should have been 4 ohms. Yeah, that seemed large to me at the time, but I thought maybe I just set up a weird problem. But apparently that's not the case. So let me find this guy again real quick. So our process is right. I just made a simple mathematical error. My apologies for that. So 3 over 5 quantity squared times 2 plus 4 I, and then putting that into rectangular form comes out to be 18 over 25 plus 36 over 25. So let's change that, and then I'm going to put this back into my calculator, and hopefully this time we get the correct answer. For what it's worth, Jude, I did get the same answer that you did, but it was wrong. So, all right, let me try this again. My apologies for the calculation mistake on the easy part. So now I got 7.72390. So let's call that 724 with an angle of 24.050 degrees. Did I? amps. I'm wondering when I solved this previously, because I'm off by exactly 5 degrees. So I may have not been paying attention when I solved it, and I might have said that this was 45 angle 30 or something like that. So if the voltage comes out to be off exactly 5 degrees, I just use 30 degrees instead of 35 because I wasn't paying enough attention when I solved this previously. Our magnitude is right. Our phase angle is exactly 5 degrees off. So I feel like that's just an error in my part when I solved it originally. This process is correct. Okay. So now that we know what this I1 is, what would V1 be? Yeah, exactly right. So that I1 that we just solved for times that 18 over 25 plus J 36 over 25. So I'm just typing that into my calculator. And I get 12.435 with an angle of 87.485 degrees volts, which is just 5 degrees off from that guy. So I think I just put 30 degrees in when I solved it previously on accident. Okay. So now that I know, let me do shift store B. So now that I know I1 and V1, how could I solve for I2 and V2? Well, I'm just going to use these two relationship right here. I don't have to do any extra work at all, right? So V2 is literally just going to be V1 over 3/5, right? Which I get to be 20.725 with an angle of 87.485 degrees. And then I2 is just A 3/5 times I1. Yep. Which came out to be 4.634 with an angle of 24.050 degrees amps. For what it's worth, technically we wouldn't be finished with this problem. We would have one more step to do. And that step would be converting these signals from the frequency domain back into the time domain, which is where these answers are. Okay. So that's literally just taking that magnitude, taking that phase angle, and adding back in the cosine 200t plus part. Okay. Like one. Yeah. So not a huge thing. Yeah. But if I ask you for an answer in the time domain, then you only get full credit if you give me the answer in the time domain. But you've done 90% of the work if you do it in the frequency domain. So I'm not going to heavily penalize that at all. Okay. So anybody have any questions about this guy right here? Okay. So let's look at problem 2. Okay.
Yeah, question.
Sure.
So you flip the dot and the sign. You can just do that really at any time.
Yeah. So I didn't really flip the dot and the sign. Well, I mean, I did. But how I envision it is I literally took that whole secondary side of the circuit and just turned that whole thing over. So in doing that, that flipped the dot, it flipped the sign, and it also flipped the direction of the current. So if I flip everything, I'm good to go. Yeah. All right. So we've got this circuit right here, and it's already in the frequency domain for us. So realistically, we could apply an approach very similar to what we did with the previous problem, except that the network that we have connected on the primary side looks pretty different, okay? So how could we make this network on the primary side look more similar to the one that we dealt with in the last problem? So, so the minus J1 ohm impedance is in parallel with our coil, but it's not in parallel with the 2 ohm resistor, nor is it in series with the 2 ohm resistor. So there's not an obvious just impedance combination way to do this, okay? So in our class meeting on Tuesday, we talked about Thevenin equivalent circuits, right? So for what it's worth, this network, let me put a bubble around it. Right here looks like a Thevenin equivalent circuit because it's a voltage source in series with an impedance, right? Thevenin equivalents are voltage sources in series with a resistance or impedance. Norton equivalent circuits are a current source in parallel with an impedance. So I think that the easiest way to work this problem is actually to just draw a dashed line right here and then find the Thevenin equiv of everything to the left. And then we have essentially the exact same circuit that we just worked with just different numbers. So this is probably the easiest way to make this circuit look like every other thing that we're going to work with these transformers. Okay. So how would I find the Thevenin equivalent voltage? So I've got my 10 angle 30 degrees voltage source in series with a 2 ohm resistor in series with a minus J1 ohm capacitor. And when I'm finding Thevenin voltage, I am finding the open circuit voltage. So I'm just trying to find the voltage drop across those two terminals I get when I essentially disconnect that network to the left of the green line from the rest of the network. So how could I find this voltage VTH? So I see a voltage source in series with two impedances. We could, but I'm lazy. I want to do it in one step instead of two. So I want to do voltage division. Yeah. So we could do Ohm's law to find the current flowing around that loop, and then do I times minus J1 to get the result. That's two steps. I'm lazy, and if I can do it in one step, I want to do it in one step. So I would say that this is 10 angle 30 degrees volts. The impedance I'm trying to find the voltage drop over is that minus J1 ohm impedance. And what's the total series impedance seen by that voltage source? Just 2 minus J1. So there's my Thevenin voltage. Now I'm just going to throw this into my calculator. So 10 angle 30 times minus 1I over 2 minus 1I. And I wound up getting 4.472 with an angle of negative 33.435 degrees volts. 10 angle 30, 2 minus J1. Okay. To find my Thevenin equivalent impedance, I need to be looking at that exact same network, except that I have to turn that voltage source off. So that's going to be, this guy right here is a short circuit now. Excuse me. Here's my 2 ohm resistor. Here's my minus J1 ohm capacitance. And I'm looking in to find my Thevenin voltage, or excuse me, my Thevenin impedance. So what do I see when I look into those terminals? I think they're in parallel. Yep. So that's going to be minus J1 times 2 over minus J1 plus 2. So I'm going to throw that into my calculator real quick. Just for what it's worth, I have that as A. So 2 times negative 1 I over 2 minus 1 I. I get that to be 2/5 minus J 4/5 of an ohm. Did anyone else get that result in polar form? Okay. All right. Yes, sir. Sure. So the easiest way to explain why it's in parallel is to identify our nodes, okay? So I have this node right here, and then I have this node right here. Since both of the elements are between the pink node and the orange node, they have to be in parallel because they share both nodes. If they were in series, they would only have one common point of interconnection between them. So from here, I could replace everything to the left of that dashed line with that Thevenin equivalent circuit, okay? So that would be a 4.472. I didn't give myself enough room there. Let me scooch it over. 4.472 angle negative 33.435 degrees volt source in series with a 2/5 minus J 4/5 ohm impedance. And then I would have my primary coil, my secondary coil, and then looking at this guy, I'm just going to call this 4 plus J4. let me look at my turns ratio here. So I have 1 on this side, 2 on this side. This is my V1. This is my V2. This is my I1. And this is my I2. So what would I do now? I'm sorry, what was that? Yeah, so I'm going to refer that secondary impedance over to the primary side, right? So that is going to look like 4.472 with an angle of negative 33.435 degrees volts. Here's my 2/5 minus J 4/5 ohm resistance. This is going to be A squared times 4 plus J4. Well, what's A in this case? 1/2, so 1/2. So 1/4 times 4 plus J4 is just going to be 1 plus J1. And then here is that voltage V1, and here is that current I1. Okay. So for what it's worth, we could solve for the current first, but I want you guys to get a little bit more comfortable with voltage division because it's not jumping out at you when you can use it. So I'm going to use voltage division to solve for that voltage V1 here, okay? So I would say that V1 is going to be that 4.472 with an angle of negative 33.635 degrees volts times 1 plus J1 over 2/5 minus J 4/5 plus 1 plus J1, like so. Okay. So A times 1 plus 1I over 0.4 minus 0.8I.
I think you wrote the voltage down. You wrote it as 635, it's 435.
Thank you. And I wound up getting 4.472 with an angle of 3.435 degrees. Volts. And it looks like this time I didn't screw it up when I solved it a year ago or whatever. Okay. So from here, how can we get I1? Ohm's law, okay? So we could either do the V1 that we just found divided by that 1 plus J1, or we could do V Thevenin divided by those two impedances in series, and either way is going to give us our answer. So I'm just going to use V1 over 1 plus J1. And I got 3.162 with an angle of negative 41.565 degrees amps. Yep. We would find V2 by simply doing V1 over A1 or A, I believe. Let me double check the notes here. So this is the situation that we have. Yeah, so V2 is V1 over A. So dividing by 1/2 is the same thing as just multiplying by 2. So I get 8.944 with an angle of 3.435 degrees volts. And then for what it's worth, I2 over here is just going to be A times I1. So that's just my current divided by a factor of 2. Which I get to be 1.581 with an angle of negative 41.565 degrees amps. Let me just double check. Yep, everything checked out there. So the hardest part of this one to me was the part where we had to make it look like the things that we've done before, right? Okay. For what it's worth, there is essentially a different way to do it if you were so inclined. What we could have done, I'm just going to talk our way through this. I'm not going to bother with doing it, is we could have just referred this impedance over from the jump, and that would have left behind the following circuit, 10 angle 30 degrees volts. Here's our 2 ohm, our minus J 1 ohm, and then this guy over here would have been 1 plus J1 ohm, where this voltage would have been V1 and this current would have been I1. And we could have solved for that voltage V1 using voltage division and then use Ohm's law to solve for that current I1. But to me, this doesn't quite reinforce the way that I would prefer you to do it, where we just make everything look like all of our example problems and then go from there. So I wanted to make you aware of it, but I would prefer that you worked it out the way that we actually did. Yes.
How, so, how, how did you get do the one plus one and not like
So essentially, I'm using Ohm's law either way, right? So I know the voltage drop across just this guy right here. And I know that the same current is flowing around that loop. So I'm going to get the same result if I just take this voltage across that single impedance or the total voltage across the total impedance because they're in series. So if you plugged in or if you're more comfortable with doing that 4.472 yada, yada, yada over those two in series, that's perfectly fine. You'll get the exact same result. Any other questions about this one? All righty. So for this guy right here, this is just applying essentially everything that we have learned at this point, with our ultimate goal being to find the output voltage drop across that 10 ohm resistor. Okay. So I'm going to just kind of annotate this circuit here from the jump to kind of convert it into the frequency domain, and then we'll simplify it and all of that kind of stuff. So what would the phasor value of our source voltage be in this case? So our angle is 0. What's our magnitude? 15. So it's just 15 angle 0. What is our 6 millihenry inductor going to look like in this case? So what's omega here? 800, okay. So 800 times 0.006 comes out to be 24 over 5J. Okay. What's our 12 millihenry inductor going to look like? So there's nothing wrong with that, but since 12 is twice as large as 6, we could just double that impedance and get it without having to do much thought. So that would just be J 48 over 5 ohms. Okay. So for this particular circuit, we aren't given the polarity for our primary or secondary voltage, and we aren't given the direction for our primary or secondary current. So we get to choose those things. I would tend to choose V1 positive polarity on top, V2 positive polarity on top, I1 and I2 like this, just so that it's that case that we've been doing over and over again, right? So essentially, I could reduce this circuit down to 15 angle 0 degrees volts in series with a 2 plus J 24 over 5 ohm impedance. Here's my primary coil having 2 turns. Here's my secondary coil having 5 turns. And I'm going to leave this guy as the J48 over 5 in series with 10 ohms, at least for right now. Now I'm going to label some things. So here's our V1 and I1. Here's our V2 and I2. And this is our phasor voltage, V out. So I know that we haven't calculated V1, V2, I1, or I2 yet, but assuming that we knew those quantities, because we've worked 2 examples where we solve for those quantities, how could we use that information to get V out? So if we're going to use Ohm's law, I think it would be I2 in the resistor. Or we could do voltage division and use V2 and the resistor, right? So we could say, just for what it's worth, that after we do the same steps that we've done for these other example problems, V out that we're looking for is just going to be I2 multiplied by 10 ohms, or that's going to be the exact same thing as V2 times 10 ohms over 10 plus J 48 over 5 from voltage division. Either way will give us the answer that we're looking for. Okay. So I've got this circuit simplified down to, impedances connected to an ideal transformer and all that kind of stuff. So what should my next step be here? Yep, exactly right. So that's going to look like 15 angle 0 degrees volts. Here's 2 plus J 24 over 5 ohms. This is going to look like, actually, let me put it as A squared times 10 plus J 48 over 5, like so, where A in this case is just 2/5, so I'll have 2 over 5 squared multiplied by 10 plus 48i over 5. Converting that into rectangular form, I get 8 over 5 plus 192 over 125 ohms. Sorry, that should be a J there. This guy is V1, this guy is I1. And realistically, we only actually need to solve for one of these two things, because if we know the primary voltage, then we know the secondary voltage, and we can use the secondary voltage to find V out. Or if we know the primary current, then we can find the secondary current, and then we can use the secondary current to find V out. So realistically, we get to do less work on this one. So which would you rather find, V or I, for this circuit? I1, okay? So I1, using Ohm's law, is just going to be 15 angle 0 degrees volts divided by that 2 plus J 24 over 5 ohms plus that 8/5 plus J 192 over 125 ohms. And so I'm going to throw that into my calculator. And if I type things in correctly here, I got 2.058 and some change with an angle of negative 60.396 degrees amps. How do I get I2? So just A times I1. Yep. So A times I1, where A in this case is just 2/5. So I'm just going to multiply that answer by 2/5. And I get 0.823 and some change with an angle of negative 60.396 degrees amps. And then lastly, I need to calculate V out. And since I found the current, I'm just going to multiply that by 10 ohms. So that's just I1 times 10 ohms gives me 8.233 with an angle of negative 60.396 degrees volts. Oh, you're absolutely right. Thank you for that. I used the value of I2. I wrote down I1. Thank you. So what do you guys think about these problems? Pretty straightforward, right? So when I assign you a homework about this, I'm going to say later today, but honestly, it's going to be sometime this weekend when I have time to actually think about the damn thing. Really, the only thing that I can throw to kind of mess this stuff up is putting dots on opposite sides or changing the directions of a current or something like that. And because we literally have notes on how to treat every single one of those cases, it's really just the same thing, except that sometimes you're going to have a negative sign in your conversion from going from primary voltage to secondary voltage or primary current to secondary current. Everything else is going to be the same. Okay. All right, I'm more than happy to work more example problems if you guys want to. We've got an hour left. I can answer questions about your homework assignment that I think might be due tonight, something like that.
One thing I was